Let's talk about something that doesn't always make the headlines when we discuss farming, but absolutely should. Energy. Not as some abstract concept, not as a line item buried in a spreadsheet, but as one of the most critical inputs that determine whether a modern farm succeeds or struggles. When we think about what a farm needs to operate, we often picture seeds, fertilizer, water, and labor. And yes, those are all essential. But here's what many people outside agriculture don't fully grasp. None of those inputs matter without energy. Energy is an invisible thread that connects every single operation on a modern farm. Think about it this way. That irrigation pump that keeps your crops alive during a dry spell, it runs on electricity or diesel. The tractor that tills your fields, plants your seeds, and harvests your crops, fuel. The refrigeration units that preserve your produce from spoiling before it reaches a market, electricity. The grain dryers that prevent mold and maintain quality, more electricity. Even the lighting in your chicken houses, the climate control in your greenhouses, the automated feeding system for livestock, all of it demands a constant, reliable flow of energy. In traditional accounting, energy often gets categorized as overhead, as if it's somehow separate from the core business of growing food. But that's a fundamental misunderstanding of modern agriculture. Energy is an overhead. It's a primary input, just as essential as the soil beneath your feet. Without energy, precision agriculture doesn't exist. Without energy, we're back to subsistence farming with hand tools. Let's put some real numbers to this. A mid-sized dairy farm in Wisconsin might spend anywhere from $50,000 to over $100,000 annually just on electricity. That's powering milking equipment, refrigeration, ventilation systems, and lighting. A large-scale irrigation operation in California's Central Valley could burn through tens of thousands of gallons of diesel every growing season, just to move water from source to field. For greenhouse operations in colder climates, heating costs alone can represent 30 to 40% of total operating expenses. Now, here's where things get really challenging for farmers. Energy prices don't rise in isolation, and farmers don't have the luxury of simply passing costs along to consumers the way other industries might. When global oil prices spike, farmers feel it immediately. Diesel for tractors and irrigation pumps gets more expensive overnight. But here's the brutal reality. Farmers can't just call up the grocery store and say, "Hey, wheat costs more to produce now, so pay me more per bushel." That's not how agricultural commodity markets work. In most cases, farmers are price takers, not price makers. They sell into global markets where prices are determined by supply, demand, weather patterns around the world, currency fluctuations, and countless other factors beyond any individual farmer's control. So when your input costs rise by 20 or 30% because of energy price spikes, but the price you receive for your corn or soybean stays flat or even drops, your profit margins get crushed. Let me give you a concrete example. In 2022, when energy prices surged globally following geopolitical disruptions, farmers across North America and Europe saw their fuel costs nearly double in some cases. A farmer in Iowa who might have budgeted $40,000 for diesel suddenly faced bills closer to $70,000 or $80,000. Meanwhile, corn prices, while elevated at certain points, didn't rise proportionally or consistently enough to offset those increased costs. The result? Dramatically reduced profitability, and in some cases, actual losses for the season. And it's not just direct fuel costs. When energy prices rise, so does everything else. Fertilizer production is extremely energy intensive. Natural gas is a primary feedstock for nitrogen fertilizer. When natural gas prices spike, fertilizer prices follow right behind. Transportation costs increase because trucks and trains run on diesel. Processing costs go up, storage costs climb. It's a cascade effect, and the farmers stand at the bottom of the waterfall, absorbing all that pressure. Here's another dimension most people don't consider. Farmers often have to commit to planting decisions months before they harvest and sell their crops. They're making energy-intensive investments in spring, planting and irrigating and fertilizing based on price expectations that may not materialize by fall. It's a constant gamble, and energy volatility makes that gamble far more risky. Food prices do eventually reflect these increased costs, but there's usually a significant lag. And the price increase that consumers see at the grocery store often doesn't translate back to proportional increases in what farmers actually receive. The supply chain captures much of that price adjustment. So when we talk about energy costs in agriculture, we're really talking about food security and farm viability. Stable, affordable energy isn't just good for farmers' bottom lines. It's essential for stable food supplies and reasonable food prices for everyone. But here's where the story gets interesting and, frankly, a lot more hopeful. Farms aren't just energy consumers. They have the potential to be significant energy producers. And that dual role, consumer and producer, puts agriculture in a unique position that almost no other industry can claim. Think about what a farm actually is from a physical standpoint. It's usually a large amount of land, often with relatively few obstructions. It has structures like barns and equipment sheds with expansive roof surfaces. It's located in rural areas where wind can flow unimpeded across open landscapes. Many farms have access to organic waste materials, animal manure, crop residues, that can be converted into energy through various processes. In other words, farms are sitting on enormous untapped energy potential. This isn't just theoretical. Farmers around the world are already transforming their operations into hybrid agricultural energy businesses. And they're doing it in ways that don't compromise their primary mission of producing food. In many cases, adding energy production actually enhances agricultural productivity and resilience. Consider a corn and soybean farmer in Illinois who installs solar panels on the roofs of his grain storage facilities. Those panels generate electricity that offsets the farm's consumption, reducing monthly utility bills. In months when the panels produce more electricity than the farm uses, that excess gets sold back to the grid, creating a new revenue stream. The grain bins still store grain. The core business hasn't changed. But now there's an energy business running alongside it, providing income diversification and price hedging. Or think about a dairy operation in upstate New York that installs an anaerobic digester to process manure from its herd. The digester produces biogas that can be burned to generate electricity and heat. The farm uses some of that energy for its own operations, reducing what it needs to purchase from utilities. The remaining energy gets sold. And as a bonus, the digestion process produces a nutrient-rich fertilizer byproduct that goes back on the fields. It's a closed-loop system that turns a waste management problem into an energy asset. The economic logic here is compelling. Farmers already own the land. They already have the infrastructure. They're already managing complex operations that require coordination of multiple systems. Adding energy generation leverages existing assets and capabilities. But there's a deeper strategic advantage, too. By producing their own energy, farmers reduce their exposure to energy price volatility. When diesel prices spike, a farmer with solar-powered irrigation isn't as vulnerable. When electricity rates climb, a farm with its own wind turbine or solar array maintains more stable operating costs. Energy production isn't just about new revenue. It's about resilience and risk management. And let's think bigger picture for a moment. Rural areas, where most farms are located, often have aging electrical infrastructure and limited grid capacity. Distributed energy generation on farms can actually strengthen rural power systems, provide local energy security, and reduce the need for expensive transmission infrastructure. Farms producing energy isn't just good for individual farm businesses. It's good for rural communities and regional energy systems. So let's dive into the specifics. How exactly are farms using solar energy today? What does it look like in practice? Solar adoption in agriculture comes in several distinct forms, each suited to different types of operations and objectives. The simplest and often the first step is rooftop solar. Farms have a lot of roof space. Barns, equipment sheds, grain storage buildings, packing facilities. These structures often have large, south-facing roof areas that are perfect for solar panel installation. A typical dairy barn might have 5,000 square feet of roof space. Cover that with solar panels, and you could generate enough electricity to offset a substantial portion of the farm's energy consumption, sometimes 50% or more depending on the farm's energy use patterns and the solar resource in that location. Rooftop solar has some real advantages. It doesn't consume productive agricultural land. It makes use of existing structures. Installation is relatively straightforward. And in many regions, there are financial incentives, tax credits, grants, or favorable loan programs specifically designed to encourage renewable energy adoption in agriculture. A vegetable farm in North Carolina, for instance, might install solar panels on its packing shed. That facility runs refrigeration units, conveyor systems, washing equipment, all energy-intensive operations. With rooftop solar, the farm can dramatically reduce its electricity bills during peak production season, when both solar generation and energy consumption are highest. The payback period might be 6 to 8 years, after which the electricity is essentially free for the remaining lifespan of the panels, typically 25 years or more. Then there's ground-mounted solar. This is where panels are installed on fixed structures or tracking systems in open field areas. Ground-mounted systems offer more flexibility in terms of size and orientation compared to rooftop installations. They can be scaled up significantly, potentially generating far more electricity than the farm itself consumes, with excess sold back to grid. A grain farm in Indiana with several hundred acres might dedicate 5 or 10 acres to a ground-mounted solar array. That's a relatively small percentage of the total farm area, but it could generate hundreds of kilowatts of power, enough to cover all farm electricity needs and create surplus for sale. The land under and around the panels can often still be used for grazing sheep or for pollinator habitat, adding additional value. The economics of ground-mounted solar have improved dramatically over the past decade. Panel costs have dropped by more than 70% since 2010. Installation expertise has grown. Financing options have expanded, and in many markets, the combination of reduced utility bills and revenue from selling excess power makes the investment pencil out quite favorably. But here's an important consideration. Ground-mounted solar does use land. For farms where every acre of crop production counts, taking land out of agricultural use for solar can be a difficult decision. That's where the next evolution comes in. Agrivoltaics. It's a term you're going to hear much more often in the coming years, and it represents one of the most exciting innovations at the intersection of agriculture and renewable energy. The concept is elegantly simple. Instead of choosing between farming and solar energy production, you do both on the same land at the same time. You install solar panels elevated high enough and spaced appropriately so that crops can grow underneath or livestock can graze beneath and around them. Now, you might be thinking, wait, don't crops need full sunlight? How can they grow in the shade of solar panels? Great question. And the answer is more nuanced and more interesting than you might expect. First, not all crops need full, uninterrupted sunlight all day long. Many crops, particularly leafy greens, certain herbs, berries, and shade-tolerant vegetables, can actually thrive with partial shading. In fact, in hot, arid climates, some crops suffer from too much direct sun exposure. They experience heat stress, excessive water loss through transpiration, and reduced productivity. The partial shade provided by solar panels positioned overhead can create a more favorable microclimate, reducing heat stress, lowering water requirements, and in some cases, actually increasing crop yields compared to fully exposed growing conditions. Research from institutions like the University of Arizona has demonstrated this effect quite convincingly. In trials growing tomatoes, peppers, and chard beneath solar panels in the Arizona desert, researchers found that the shaded crops use significantly less water and, in many cases, produce higher yields than control crops grown in full sun. The panels created cooler conditions underneath, reduced soil moisture evaporation, and protected plants from the most intense midday heat. The panels themselves also benefit. Standard solar panels lose efficiency when they get too hot. In hot climates, panel temperatures can exceed 150 degrees Fahrenheit, significantly reducing power output. But when panels are installed over crops, the vegetation beneath creates a cooling effect. The plants transpire, releasing water vapor that cools the air around the panels. Studies have shown that this cooling can improve panel efficiency by 10% or more compared to panels over bare ground or gravel. So agrivoltaics creates a win-win. The crops get a better growing environment. The panels produce more electricity. And the land serves a dual purpose, producing both food and energy. Now, agrivoltaics isn't universally applicable. You can't grow corn or wheat beneath solar panels, at least not with current panel heights and spacing. Those crops need full sun and grow too tall. But for the crops and agricultural activities where it does work, the model is incredibly compelling. Grazing livestock beneath and around solar arrays is another proven application. Sheep, in particular, work beautifully in this system. They keep vegetation managed around the panel supports, reducing mowing and maintenance costs for the solar operator. And from the farmer's perspective, they get grazing land that also generates electricity revenue. There are already commercial-scale examples of this in operation. Solar farms in the United Kingdom, for instance, routinely graze sheep beneath panels, creating income from both electricity sales and livestock. The infrastructure requirements for agrivoltaics are a bit more complex than standard ground-mounted solar. Panels need to be mounted higher, typically 8 to 12 feet off the ground, to allow for equipment access and adequate light penetration. Spacing between panel rows needs to be wider. But as the model proves itself economically, engineering solutions are becoming more refined and costs are coming down. Let's shift focus slightly and talk about one of the most immediate and impactful applications of solar energy in agriculture: irrigation pumping. Irrigation is the lifeblood of agriculture in many of the world's most productive farming regions. Without it, vast areas that now produce abundant food would be semi-arid scrubland. But irrigation is also one of the most energy-intensive activities on a farm. Moving water, especially pumping groundwater from deep wells or lifting surface water to elevated fields, requires substantial power. Traditionally, this power has come from two sources: diesel engines and grid electricity. Both have significant drawbacks for farmers. Diesel irrigation pumps are mobile and independent from the grid, which is useful in remote field locations. But diesel is expensive, prices are volatile, and diesel engines require regular maintenance. They're also noisy and produce emissions. For a large irrigation operation, fuel costs can run into tens of thousands of dollars per season. Grid-connected electric pumps avoid fuel volatility, but they come with their own issues. In rural areas, grid power may be unreliable. Connection costs for remote fields can be prohibitive, and utility demand charges, fees based on peak power consumption, can make agricultural electricity very expensive. When your irrigation pump draws maximum power during the hottest part of the day, exactly when grid demand is highest, you get hit with premium rates. Enter solar-powered irrigation. The basic concept is straightforward. Solar panels power an electric motor that drives the irrigation pump. During sunny days, when crops need water most, solar panels produce maximum power. The match between when solar generates the most electricity and when irrigation demands the most water is nearly perfect. Let's walk through a real-world example. A cotton farmer in West Texas has several center pivot irrigation systems drawing water from the Ogallala Aquifer. Historically, those pivots ran on diesel engines. The farmer was spending roughly $30,000 per year on diesel fuel. Rising fuel costs were eating into already thin margins. The farmer partnered with a solar installer to design a photovoltaic system sized to match the power requirements of the irrigation pumps. The installation cost was significant, around $150,000 for the complete system. But with federal tax credits, state incentives, and financing options, the effective out-of-pocket cost was reduced substantially. Once operational, the solar system eliminated nearly all diesel fuel expenses. Based on current fuel prices and solar production, the payback period is projected at 7 to 9 years. After that, irrigation energy costs drop to essentially just maintenance and eventual equipment replacement. Beyond the direct cost savings, there are operational benefits. Solar irrigation systems are quieter. They require less frequent maintenance than diesel engines. There's no risk of fuel theft, which is a real concern in some remote agricultural areas. And there's an environmental aspect, eliminating diesel emissions and reducing the carbon footprint of the farming operation. Water and solar have another synergy worth noting: water storage as energy storage. Some solar irrigation systems are designed to pump water into elevated storage tanks or reservoirs during peak solar production hours. That stored water can then gravity feed to the crops during evening or cloudy periods when solar production drops. Essentially, you're using water storage as a battery, storing the energy in the form of elevated water potential rather than in chemical batteries. It's an elegant, low-tech solution that's been used for over a century, but pairs beautifully with modern solar technology. The scalability of solar irrigation is impressive too. Small-scale market gardens can use just a few solar panels to power drip irrigation systems. Large commercial farms can deploy megawatt-scale solar arrays to drive massive irrigation infrastructure. The technology adapts across the full spectrum of agricultural operations. In developing regions, solar irrigation is genuinely transformative. Smallholder farmers who previously relied on hand watering or rain-fed agriculture can access reliable irrigation for the first time. Without the need for diesel fuel purchases or grid connections, solar pumps lower the barrier to entry for improved agricultural productivity. Organizations working on international development and food security increasingly see solar irrigation as a key technology for improving agricultural resilience in vulnerable regions. Now, solar energy has an obvious limitation. The sun doesn't shine at night. Cloud cover reduces output. Seasonal variations mean much less solar production in winter than in summer. For a farm that needs electricity 24/7, for milking cows at 5 in the morning or running ventilation fans in poultry houses overnight, solar alone isn't enough. This is where energy storage enters the picture. And while batteries might seem like a technology more associated with electric cars or consumer electronics, they're increasingly relevant and viable for agricultural operations. Let's talk about why energy storage matters specifically for farms. First, many farms are located in rural areas where grid electricity can be unreliable. Storms, aging infrastructure, long distribution lines. These factors mean power outages are more common in rural areas than in urban centers. For some agricultural operations, even a short power outage can be catastrophic. Dairy farms need to milk cows on schedule. Poultry operations need continuous ventilation. Greenhouse operations need climate control. A few hours without power can mean spoiled milk, dead livestock, or ruined crops. Traditionally, farms have dealt with this using diesel backup generators. And generators serve that purpose, but they're expensive to run. They require fuel storage, they need regular maintenance, and they only kick in during outages, providing no value the rest of the time. Battery storage offers a different model. A properly sized battery system, paired with solar panels, can store excess solar energy generated during the day and release it at night or during cloudy periods. The farm becomes much less dependent on the grid. In some cases, farms can go completely off-grid, rely entirely on their own solar plus storage system. Even for farms that remain grid-connected, batteries provide resilience. When the grid goes down, the battery automatically takes over, providing seamless backup power. Unlike a generator that might take minutes to start and requires manual intervention, a battery system transitions instantly and automatically. There's also an economic angle. In many electricity markets, utility rates vary by time of day. Power is more expensive during peak demand hours, typically late afternoon and early evening. Batteries allow a farm to store cheap electricity, either from their own solar panels or from the grid during low-demand periods, and then use as stored energy during peak price hours, avoiding the highest rates. This practice, called load shifting or peak shaving, can result in significant savings on electricity bills. Let's look at a case study. A mid-sized dairy farm in Vermont installed a solar array combined with a lithium-ion battery system. The total system size was about 100 kilowatts of solar and 75 kilowatt-hours of battery storage. During the day, the solar panels generate electricity that powers farm operations and charges the batteries. Excess power goes back to the grid. At night, the batteries discharge to power critical loads like milking equipment and refrigeration. The farm's utility bills dropped by roughly 60%. During several winter storms that knocked out grid power for hours, the farm maintained full operations without resorting to the diesel generator that had previously been their only backup. The system paid for itself in just under 10 years, and the batteries are warranted for 15 years of operation. Battery technology for these applications has advanced rapidly. Lithium-ion batteries, the same chemistry used in electric vehicles, have become the dominant choice for farm-scale storage. They're efficient, They have good energy density. They can charge and discharge thousands of times, and costs have dropped dramatically. 10 years ago, battery storage was prohibitively expensive for most farms. Today, with falling costs and available incentives, it's increasingly within reach. Alternative battery chemistries are also emerging. Flow batteries, which store energy in liquid electrolytes, offer potential advantages for long-duration storage. Saltwater batteries provide a non-toxic, environmentally friendly option. As the technology continues to evolve, farms will have even more options tailored to specific needs. One important point: battery storage isn't just for farms with solar panels. Even a farm that doesn't generate its own electricity can benefit from batteries by purchasing cheap grid power during off-peak hours, storing it, and using it during expensive peak hours or during outages. The economic case varies by location and utility rate structure, but in many markets, it's already viable. Looking ahead, as electric farm equipment becomes more common, tractors, UDVs, even larger machinery, on-farm battery storage will serve double duty, both stabilizing farm energy systems and charging electric equipment. The integration of storage generation and electrified equipment creates a comprehensive energy ecosystem right on the farm. Solar gets a lot of attention, and rightfully so, but it's not the only renewable energy resource available to farmers. Wind energy has been part of agriculture for over a century. Those classic American windmills that pumped water for livestock were wind turbines, just a simpler, older form. Today's wind turbines are far more sophisticated, but the basic principle remains the same: convert the kinetic energy of moving air into usable power. Let's cover the fundamentals of how modern wind turbines work. At the most basic level, wind turbine blades are shaped like airplane wings. When wind flows over blades, it creates lift, similar to how an airplane wing generates lift. That lift force causes the blades to rotate. The rotating blades turn a shaft inside the turbine nacelle, the box at the top of the tower. That shaft connects to a gearbox, which increases the rotational speed, and then to a generator. The generator converts the mechanical rotation into electricity. The amount of power a wind turbine can generate depends on several factors. Wind speed is the most critical. Power output increases with the cube of wind speed. That means if wind speed doubles, power output increases eightfold. This is why even small differences in average wind speed make enormous differences in energy production. A site with an average wind speed of 15 miles per hour will produce dramatically more energy than a site averaging 12 miles per hour. Turbine size matters too. Larger blades sweep a larger area, capturing more wind energy. Tower height is important because wind speeds are generally higher and more consistent at greater heights above the ground. Surface friction from trees, buildings, and terrain features slows wind near the ground. Get up to 100 or 150 feet, and wind becomes stronger and more laminar. Modern utility-scale wind turbines, the kind you see in large wind farms, can be massive, towers 200 to 300 feet tall, with blades over 150 feet long. Each turbine can generate multiple megawatts of power, enough to supply hundreds or even thousands of homes. But for agricultural applications, we're usually talking about smaller turbines. A farm-scale wind turbine might have a tower 50 to 150 feet tall, blades 20 to 50 feet long, and generate anywhere from 10 kilowatts to 100 kilowatts or more, depending on design and wind conditions. The power from the turbine comes out as AC electricity, but often at a voltage or frequency that's not directly usable. An inverter, similar to those used in solar systems, converts the electricity to match grid standards or the farm's electrical system requirements. If the turbine is grid connected, any excess power can be sold back to the utility. If it's part of an off-grid system, the power either gets used immediately, stored in batteries, or dumped into a resistive load like a water heater. Wind turbines are most efficient when the wind is steady and within a certain speed range. Too little wind, and the turbine doesn't turn. Too much wind, and the turbine has to shut down or feather its blades to avoid damage. Most turbines are designed to operate optimally with wind speeds between 10 and 30 miles per hour. This is called the turbine's power curve, and it's a critical specification to understand when evaluating whether wind makes sense for a particular site. One of the beautiful things about wind energy is that it often complements solar. Wind frequently blows more at night and during winter months, exactly when solar production is lowest. On a farm with both solar panels and a wind turbine, the two systems can provide more consistent energy production across daily and seasonal cycles than either technology alone. So, if a farmer is interested in wind energy, what are the options? There are really two distinct pathways: installing a small to medium-sized turbine on a farm for direct use, or participating in a utility-scale wind farm development. Let's talk about on-farm wind turbines first. These are turbines a farmer owns and operates, typically generating 10 kilowatts to a few hundred kilowatts of power. The electricity powers farm operations directly, with excess sold to the grid if the farm is grid connected. The economics here depend heavily on local wind resources and electricity prices. A farmer in a windy area with high electricity rates has a much stronger case for on-farm wind than a farmer in a low-wind region with cheap power. As a general rule, for on-farm wind to make economic sense, you want average wind speeds at least 11 or 12 miles per hour hub height, and electricity costs above 10 or 12 cents per kilowatt hour. Installation costs for small to medium farm-scale turbines typically run from $4,000 to $8,000 per installed kilowatt of capacity. So a 50-kilowatt turbine might cost $200,000 to $400,000. All in, that's a significant investment, though incentives, grants, and tax credits can reduce the effective cost considerably. Payback periods range widely, from 8 to 20-plus years, depending on wind resource, electricity prices, and incentives. On-farm wind has some distinct advantages. The farmer retains full control. They directly benefit from reduced electricity costs and sale of excess power. If the farm has high energy needs that coincide with windy periods, the value proposition is even stronger. A dairy farm with round-the-clock electricity demand, for instance, benefits every hour the turbine is producing. But there are challenges too. Wind turbines need maintenance. Bearings wear out. Gearboxes fail. Blades can be damaged by lightning or storms. Some farmers have mechanical aptitude and equipment to handle basic maintenance themselves. Others need to hire specialized technicians, which can be expensive and difficult to arrange in rural areas. There are also regulatory and permitting hurdles. Many jurisdictions have zoning rules that limit turbine height or require minimum setbacks from property lines and occupied buildings. Some homeowner associations or local communities oppose wind turbines due to aesthetic concerns or noise. Navigating those regulatory and social challenges can be as difficult as the technical and financial aspects. Now, let's contrast that with utility-scale wind development. Instead of installing and operating their own turbines, farmers lease land to wind energy developers who build and operate large wind farms. The scale is entirely different. Utility-scale turbines can each generate 3 to 5 megawatts or more. Developers typically build them in clusters, wind farms with dozens or even hundreds of turbines. The developer handles all permitting, financing, construction, operation, and maintenance. The farmer's role is simply to lease the land. Lease payments vary, but a common structure is a few $1,000s per turbine per year or a percentage of the revenue the turbine generates, often 2 to 4%. For a farmer who has multiple turbines on their land, this can represent significant income. 10 turbines at $4,000 each per year is $40,000 in annual lease income. And importantly, that income is highly stable and predictable. It doesn't fluctuate with crop prices or weather. It arrives whether you have a great harvest or drought. The land footprint is surprisingly small. Each turbine tower and access road might occupy a quarter acre or less. The farmer can continue farming right up to the base of the tower. Crops can grow, cattle can graze, all normal agricultural activities continue. Essentially, the farmer is getting paid for using the airspace above the land, not the land itself. From a risk perspective, utility-scale leasing is very low risk for farmer. There's no capital investment required, no maintenance responsibility, no technology risk. It's purely a land use agreement. However, there are trade-offs. The farmer has no control over the turbines. If they're noisy or cause issues, the farmer is still locked into the lease agreement, which typically lasts 20 to 30 years. There can be restrictions on what the farmer can build or do near the turbines. And in some cases, the presence of wind turbines affects property values or creates tension with neighbors who don't like the visual impact. Some farmers see utility-scale wind leasing as a way to diversify income and ensure the farm stays viable across generations. That stable lease income can cover property taxes, fund retirement, or support the next generation taking over the farm. Other farmers prefer to maintain full control of their land and operations, even if it means foregoing lease revenue. There's no universally right answer. It depends on the individual farm's financial situation, the farmer's priorities, the quality of the wind resource, and the availability of developers interested in the location. Wind energy isn't equally viable everywhere. Geography, climate, and terrain play enormous roles in determining whether wind makes sense for a particular farming region. Understanding these geographic factors is essential for any farmer considering wind, whether on-farm turbines or leasing for utility-scale development. The first and most obvious factor is wind speed. As we've discussed, wind speed determines power output, and power increases with the cube of wind speed. Areas with consistent, strong winds are prime territory for wind energy. In the United States, the Great Plains, stretching from Texas up through the Dakotas and into Montana, is the country's wind energy heartland. Average wind speeds in this region often exceed 13 to 15 miles per hour at turbine hub heights. The landscape is relatively flat and open, with few obstructions to disrupt airflow. It's no coincidence that this is where you see the largest concentration of both utility-scale wind farms and on-farm wind turbines. The Midwest Corn Belt also has decent wind resources, though generally not quite as strong or consistent as the Great Plains. States like Iowa, Minnesota, and Illinois have seen significant wind development, particularly utility-scale projects. Farmers in these states have been some of the most active participants in wind energy, both through on-farm installations and land leasing. Coastal areas can also have excellent wind resources. The consistent onshore and offshore breezes make coastal farms attractive for wind development. However, coastal land is often more expensive and may have competing uses, like residential or commercial development, which can complicate wind projects. Mountainous regions present a mixed picture. Ridge tops and mountain passes can have very strong winds, making them good sites for wind turbines. But terrain complexity creates turbulent, unpredictable wind patterns in valleys and on slopes. Installation and maintenance are also more challenging and expensive in rugged terrain. So while some mountainous farming areas have wind potential, it's much more site-specific than in open plains. Forested areas are generally poor for wind energy. Trees create surface roughness that disrupts wind flow and dramatically reduces wind speeds near the ground. Even tall turbine towers can struggle to get above the turbulent air layer created by forest canopy. Farms in heavily forested regions, like much of the Northeast or the Pacific Northwest, have limited wind energy potential unless they're on exposed hilltops or coastal bluffs. Climate patterns matter too. Some regions have strong seasonal wind variations. Wind might be excellent in winter and spring, but weak in summer. For a farm with year-round energy needs, this seasonality affects the value proposition. However, as we mentioned earlier, the fact that wind often peaks when solar is weakest can make them complementary. Another geographic consideration is proximity to transmission infrastructure. Even if a site has excellent wind, if it's far from power lines capable of carrying the electricity to market, development becomes much more expensive or even infeasible. Utility-scale wind developers are very focused on grid access. They'll often pass on a site with good wind if the transmission connection costs are too high. For on-farm turbines, if the farm is already grid-connected, this is less of an issue, but there may still be infrastructure upgrades required to handle the power flows. Regulatory and policy geography also plays a role. Some states have renewable energy mandates, tax incentives, or favorable net metering rules that make wind economically attractive. Other states have limited or no incentives, making the economics much tougher. For example, wind development has flourished in states like Kansas, Oklahoma, and Iowa, partly because of good wind resources, but also because of supportive state policies and cooperative utilities. Conversely, some states with decent wind resources have seen limited development due to regulatory barriers or utility resistance. Let's bring this to a specific example. A wheat farmer in western Kansas sits in one of the best wind resource areas in the country. Average wind speeds exceed 14 miles per hour. The land is flat and open. Transmission lines cross the property. This farmer could likely either install an on-farm turbine economically or attract interest from utility-scale developers for a land lease. The wind blows hard and consistent. Electricity prices in the region are moderate to high, and state policies are wind-friendly. All factors align. Now contrast that with a dairy farmer in Vermont. Wind speeds are moderate, maybe averaging 10 miles per hour, but highly variable due to terrain and forests. Transmission access is limited. Installation costs are higher due to terrain challenges. State policies are supportive of renewables, but the wind resource itself is marginal. For this farmer, solar might make far more sense than wind, even though both are renewable options. Understanding these geographic realities helps farmers make informed decisions. Wind isn't a one-size-fits-all solution. It works brilliantly in the right locations and makes little sense in others. Before investing time and money into exploring wind energy, a farmer needs to honestly assess whether their location has the wind resource to justify it. There are tools available, wind maps, local meteorological data, even on-site wind monitoring equipment that can be installed to measure actual wind speeds over time. That data-driven assessment is critical. In the end, wind energy in agriculture succeeds where geography, economics, and policy align. Where they do align, wind can be transformative, providing farmers with new income streams, reducing energy costs, and contributing to cleaner energy systems. Where they don't align, other renewable options or energy efficiency measures may be the better path forward. And that brings us to the end of this first segment. We've covered why energy is foundational to modern farming, how energy price shocks impact farmers and food prices, the unique opportunity farms have to produce energy, the various ways solar is being deployed in agriculture, the exciting potential of agrivoltaics, the practical benefits of solar irrigation, the role of battery storage in farm resilience, the basics of wind energy and how turbines work, the differences between on-farm and utility-scale wind approaches, and finally, the geographic factors that determine where wind energy makes sense. We've laid a foundation for understanding energy in agriculture, not as an afterthought, but as a central strategic consideration for the future of farming. In the next segment, we'll build on this foundation, exploring even more technologies and strategies that are reshaping how farms power themselves and contribute to broader energy systems. Let's shift our focus now to a form of renewable energy that's uniquely suited to agriculture, particularly livestock operations. We're talking about biogas. And unlike solar panels or wind turbines that harvest energy from natural forces outside the farm, biogas systems transform what many farmers consider waste into a valuable energy resource. Here's the basic premise. Farms, especially livestock operations, produce enormous quantities of organic waste. Manure from cattle, pigs, and chickens, bedding materials soiled with animal waste, crop residues after harvest, spoil feed, food processing waste if the farm has value-added operations. Historically, managing this waste has been a challenge and an expense. It needs to be stored, treated, and disposed of properly to avoid water pollution, odor problems, and regulatory violations. But organic waste contains energy. Locked within the chemical bonds of those organic molecules, carbohydrates, proteins, fats, is energy that can be released and captured. The process that does this is called anaerobic digestion. Anaerobic digestion is essentially controlled decomposition happening in an oxygen-free environment. Here's how it works. Organic waste gets fed into a sealed tank called a digester. Inside the digester, communities of microorganisms, bacteria, and archaea break down the organic material in the absence of oxygen. This biological process produces biogas, a mixture primarily composed of methane and carbon dioxide, typically about 55 to 70% methane. Methane is an excellent fuel. It's the same compound that makes up natural gas. That biogas can be burned directly to produce heat or it can fuel an engine or turbine connected to a generator to produce electricity. Some systems purify the biogas to remove the carbon dioxide and other trace components, upgrading it to nearly pure methane that can be injected into natural gas pipelines or compressed for use as vehicle fuel. Let's walk through a concrete example to make this tangible. Consider a dairy farm in Wisconsin with 800 milking cows. Those cows produce roughly 120 pounds of manure per cow per day. That's 96,000 pounds of manure daily, over 48 tons. Under traditional management, that manure gets stored in lagoons or spread on fields. It's a waste management problem. Now imagine that same farm installs an anaerobic digester. Each day, the fresh manure gets collected and pumped into the digester tank. The tank is heated to maintain optimal temperatures for the microbial communities, typically around 95 to 100 degrees Fahrenheit. The microbes go to work, and over retention time about 15 to 30 days, they break down the organic matter and produce biogas. A herd of 800 cows can generate enough biogas to produce roughly 300 to 500 kilowatts of continuous electrical power, depending on the system efficiency and manure characteristics. That's enough electricity to power the entire dairy operation, milking equipment, refrigeration, lighting, ventilation, pumps, with substantial excess power that can be sold back to the grid. In addition to electricity, the digestion process produces heat as a byproduct from the generator engine. That waste heat can be captured and used to warm water, heat buildings, or maintain the digester temperature, creating a highly efficient combined heat and power system. The digester is typically a large, insulated tank, often built partially or fully below ground. Some designs use concrete, others use steel. The tank needs to be sealed to maintain anaerobic conditions and to capture the biogas. Mixing systems keep the contents agitated to ensure uniform digestion and prevent settling or crusting. Temperature control systems maintain the ideal conditions for microbes. The biogas is collected at the top of the digester, cleaned to remove moisture and trace contaminants like hydrogen sulfide, and then piped to the power generation equipment. Safety systems monitor gas pressure and composition to prevent dangerous buildups or leaks. Methane is flammable, so proper engineering and safety protocols are essential. Different digester designs exist, each with advantages and trade-offs. Plug flow digesters work well for thick, fibrous materials like dairy manure mixed with bedding. Complete mix digesters handle more liquid waste streams and are common for swine operations. Covered lagoon digesters are simpler and less expensive but work best in warmer climates. The choice of design depends on the type of waste, climate, budget, and operational preferences. The microbial process is surprisingly robust once established. The microbes are self-sustaining as long as they're fed organic matter, kept at the right temperature, and maintained in anaerobic conditions. The system can run continuously for years with relatively minimal intervention beyond feeding waste in and removing the digestive material out. Some farms enhance biogas production by adding additional organic feedstocks beyond just manure. Food waste from grocery stores, restaurants, or food processing facilities can be co-digested with manure. These materials are often higher in energy content than manure alone, boosting biogas yields. Some farms have essentially become regional organic waste processing centers, accepting tipping fees to take in food waste while simultaneously increasing their biogas production. It's an additional revenue stream on top of the energy sales. One of the most compelling aspects of anaerobic digestion is that it solves two problems simultaneously. It addresses waste management challenges while generating renewable energy. For livestock farms, this dual benefit can be transformative. Let's talk about the waste management side first. Livestock manure, if not managed properly, poses significant environmental risks. Nutrients like nitrogen and phosphorus can leach into groundwater or run off into surface waters, causing contamination and algae blooms. Pathogens in manure can threaten human and animal health. Ammonia emissions contribute to air pollution. Methane emissions from manure storage are a potent greenhouse gas, with a global warming potential roughly 28 times greater than carbon dioxide over a 100-year time frame. Regulations around manure management have tightened considerably over the past few decades. Large livestock operations must comply with nutrient management plans, monitor runoff, and implement practices to minimize environmental impact. Violations can result in substantial fines and legal liability. Managing manure properly isn't optional. It's a regulatory and operational necessity. Anaerobic digestion fundamentally changes the waste management equation. When manure goes through digestion, several beneficial transformations occur. The process kills most pathogens, reducing disease risk. It stabilizes the organic matter, reducing odors significantly. Manure that's been digested smells far less offensive than raw manure, which is a major quality of life improvement for farm families and neighbors. The digestion process also begins to break down complex organic nitrogen into forms that are more readily plant available, improving the fertilizer value of the material, which we'll discuss more in a moment. From a greenhouse gas perspective, capturing and burning the methane in a controlled manner to produce energy is far better than letting it escape into the atmosphere from a manure lagoon. Combusting methane converts it to carbon dioxide, which still has warming potential, but far less than methane itself. Plus, you're displacing fossil fuel consumption by generating renewable energy, creating a double climate benefit. For dairy farms in particular, where manure management is a daily, year-round challenge of a large herd, digesters offer a pathway to manage waste more effectively while turning an expense into an asset. The upfront capital investment is substantial, but the long-term operational benefits, both environmental and economic, can justify that investment. The economic value extends beyond just energy sales. Some farms have been able to access carbon credit markets by documenting the methane emissions they prevent through digestion. They generate carbon offset credits that can be sold to companies or individuals looking to offset their own emissions. Depending on the carbon credit price, this can represent tens of thousands of dollars in additional annual revenue. There's also a public relations and brand value dimension. Consumers are increasingly conscious of how their food is produced. A dairy farm that can market its milk as coming from a carbon-neutral or carbon-negative operation, thanks to biogas production, may be able to command premium prices or access specialty markets. Several dairy cooperatives and processors have created sustainability programs that reward farmers for adopting practices like anaerobic digestion. Some forward-thinking farms have taken this even further, building entire circular economy systems around their digester. They accept organic waste from the surrounding community, charging tipping fees. They generate biogas for energy. They produce high-quality fertilizer from the digestate. They might even produce compressed natural gas from purified biogas for farm vehicles or for sale as transportation fuel. The digester becomes a hub of an integrated resource recovery system that generates multiple revenue streams while minimizing environmental impact. It's worth noting, though, that digesters aren't universally appropriate. They make the most sense for larger livestock operations with concentrated manure production. A farm with 50 cows probably doesn't generate enough manure to justify the capital cost and complexity of a digester. But a farm with several hundred head or more, particularly if they can aggregate manure from multiple nearby farms or accept additional organic waste, can make the economics work. Now let's talk about what comes out the other end of an anaerobic digester. After the microbes have done their work and the biogas has been extracted, what remains is a substance called digestate. And digestate is far from waste. It's a valuable agricultural product in its own right. Digestate is essentially the liquid and solid remnants of the organic material after digestion. It contains all the nutrients that were in the original feedstock, nitrogen, phosphorus, potassium, plus trace minerals and organic matter. But crucially, those nutrients are now in forms that are more stable and more plant available than they were in raw manure. During digestion, much of the organic nitrogen gets converted to ammonium, a form that plants can take up readily. This makes digestate an effective fertilizer that can be applied to cropland, much like raw manure, but with several advantages. It's more uniform in consistency, making application easier and more precise. The reduced odor means it's more neighbor-friendly to apply. The pathogen reduction means lower risk of introducing diseases to fields. Many farms use digestate as a complete or partial replacement for synthetic fertilizer. Given that fertilizer is one of the largest input costs for crop production, And fertilizer prices are closely tied to natural gas prices due to the energy-intensive Haber-Bosch process used to produce nitrogen fertilizer. Being able to produce your own biological fertilizer on-farm has real economic value. Let's quantify this. A dairy farm digesting manure from 800 cows might produce 50 to 70,000 gallons of digestate per day. Over a year, that's millions of gallons of liquid fertilizer. The nutrient content varies, but as a rough estimate, that digestate might contain the equivalent of several tons of nitrogen, a ton or more phosphorus, and multiple tons of potassium annually. Purchasing those nutrients as synthetic fertilizer could cost tens of thousands of dollars. Some farms go a step further and separate the digestate into liquid and solid fractions. The liquid fraction, which is rich in ammonium nitrogen, can be applied through irrigation systems or injected into soil. The solid fraction, which contains more of the phosphorus and organic matter, can be composted further, dried, or even pelletized into a commercial-grade organic fertilizer product. Several farms have created small businesses selling dried and packaged digestate to home gardeners, landscapers, and organic farmers. This nutrient recycling creates a closed-loop system. Crops are grown and fed to livestock. Livestock produce manure. Manure goes through digestion to produce energy. Digestate returns nutrients to the soil to grow more crops. It's a circular model that minimizes external inputs and waste outputs. It's regenerative agriculture powered by renewable energy. From a soil health perspective, digestate provides benefits beyond just nutrients. The organic matter improves soil structure, water holding capacity, and microbial activity. Over time, regular digestate application can build soil organic carbon, enhancing long-term productivity and resilience. There are regulatory considerations. Of course, digestate application is subject to the same nutrient management planning requirements as raw manure. You can't overapply and risk nutrient runoff. Application timing, rates, and methods need to be managed according to crop needs and environmental conditions. But the improved consistency and lower pathogen load of digestate can actually make compliance easier compared to raw manure management. In regions with intensive livestock production, where manure nutrients can exceed the absorptive capacity of nearby cropland, the ability to process manure through digestion and then transport the digestate further distances or concentrate it into value-added products helps address nutrient surplus challenges. It's a tool for better regional nutrient management. When we think about renewable energy leadership in agriculture, it's often livestock farms, particularly dairies and large-scale poultry operations, that are at the forefront of biogas adoption. And that makes perfect sense given the nature of their operations. Dairy farms are especially well-positioned for biogas. They have concentrated manure production from large herds housed in confined areas. They have high, continuous energy demands for milking parlors, milk cooling, water heating, and facility lighting. They often have existing manure handling infrastructure that can be adapted for digesters. And dairy farmers, as a group, tend to be sophisticated operators managing complex biological and mechanical systems, which translates well to operating biogas systems. California has been a leader in on-farm biogas adoption, driven by strong renewable energy incentives and aggressive climate policies. The state's low-carbon fuel standard provides substantial financial incentives for farms that produce renewable natural gas from biogas and use it for transportation fuel. Many California dairies have installed digesters and upgraded their biogas to pipeline-quality, renewable natural gas, selling it to fuel-compressed natural gas vehicle fleets. It's a lucrative business model that's turned many dairy farms into significant energy producers. Poultry operations, particularly large egg and broiler farms, are another segment seeing biogas adoption. Poultry litter, the mixture of manure and bedding, is nitrogen-rich and well-suited for digestion, though it requires specific digester designs to handle the drier, more fibrous material. Large poultry farms can produce enough litter to justify digester systems, especially when combined with other organic wastes. Swine operations have also been early adopters. Pig manure is very fluid and high in organic content, making it ideal for digestion. Large-scale hog farms, particularly in states like North Carolina and Iowa, have installed digesters both for environmental compliance and energy production. What's emerging is a model where livestock farms aren't just producing meat, milk, or eggs. They're energy hubs. They're processing organic waste from the broader community. They're generating renewable electricity or renewable natural gas. They're producing organic fertilizer products. The farm becomes a multi-output enterprise, diversified in a way that provides resilience and new revenue streams. Some farms have partnered with utilities or energy companies to develop and operate the biogas systems. The farm provides a feedstock and the site, while the energy company provides the capital and technical expertise. Revenue is shared. This partnership model reduces the burden on the farmer and brings in professional energy management, which can improve system performance and reliability. Regional biogas cooperatives have formed in some areas where multiple farms pool their resources and manure to support a centralized digester facility. This allows smaller farms that couldn't justify their own digester to participate in biogas production. The cooperative model spreads costs and risks while creating economies of scale. Looking internationally, countries like Germany and Denmark have developed extensive biogas sectors, with thousands of farm-based digesters operating successfully. Government policies in those countries have been highly supportive, providing feed-in tariffs that guarantee good prices for biogas-generated electricity, making the economics very attractive. The U.S. has been slower to adopt, but that's changing as policies evolve and the technology becomes more proven and affordable. So we've now covered 3 major renewable energy options for farms: solar, wind, and biogas. Each has distinct characteristics, advantages, and limitations. For a farmer trying to decide which path to pursue, understanding these differences is crucial. Let's start with cost. Upfront capital requirements vary significantly. Solar panel costs have dropped dramatically and continue to decline. A farm-scale solar installation might cost $2 to $4 per watt of install capacity. So, a 100-kilowatt system, which could offset a significant portion of a medium-sized farm's electricity use, might cost $200,000 to $400,000 before incentives. Wind turbines tend to be more expensive per unit capacity, particularly for smaller farm-scale turbines, often $4 to $8 per watt. Biogas systems are the most capital-intensive, often running into the millions of dollars for a complete digester, gas cleanup, and power generation system, though costs scale with farm size and can be more economical on a per cow or per unit waste basis for larger operations. Operating and maintenance costs also differ. Solar has the lowest ongoing costs. Panels have no moving parts, require occasional cleaning, and may need inverter replacement after 10 to 15 years, but otherwise operate with minimal intervention. Wind turbines require more regular maintenance. Gearboxes, bearings, and blades need inspection and servicing. Unexpected failures can be expensive. Biogas systems have the highest operational complexity and cost. They require daily management, feeding waste in, monitoring digestive conditions, maintaining pumps and generators, managing digestate removal. They're essentially running a biological process 24/7, which demands attention and expertise. Scalability is another key difference. Solar scales very smoothly. You can start with a small rooftop system and expand over time. You can size it precisely to your needs. Wind is less flexible. Turbines come in discrete sizes, and there's a minimum scale below which the economics don't work well. Biogas systems also have minimum viable scales. You need a certain volume of organic waste to justify the capital cost and complexity. A dairy farm with fewer than a few hundred cows typically can't justify a digester economically, though cooperative or community-scale models can lower that threshold. Reliability and dispatchability differ significantly. Solar produces power only when the sun shines. It's predictable on a daily and seasonal basis, but it's not available at night and is reduced on cloudy days. Wind produces power when the wind blows, which can be less predictable day to day, but often complements solar by being stronger at night and during certain seasons. Biogas, in contrast, is dispatchable. The biogas can be stored and burned on demand. A biogas system can provide baseload power 24/7, or it can be ramped up and down to match farm energy needs or electricity market prices. That dispatchability has significant value. Land use considerations vary too. Solar, especially ground-mounted systems, consumes land, though agrivoltaics can mitigate this. Wind turbines have a small physical footprint, but require setbacks and can affect how surrounding land is used. Biogas digesters occupy relatively small land areas, typically much less than an acre for the digester itself, plus space for digestate storage and handling. From an environmental perspective, all three reduce greenhouse gas emissions compared to fossil fuels, but the mechanisms differ. Solar and wind directly displace fossil electricity generation. Biogas not only generates renewable energy, but also prevents methane emissions from manure storage, creating a double climate benefit. For livestock farms with significant manure management challenges, biogas may deliver the greatest environmental impact. Climate and geography strongly affect suitability. Solar works nearly everywhere, but is most productive in sunny regions. Wind requires consistent strong winds, limiting where it's viable. Biogas works anywhere you have sufficient organic waste, regardless of climate, though colder climates require more energy to maintain digester temperatures. So, which is right for a particular farm? It depends on the farm's specific circumstances. A crop farm in a sunny region with low to moderate electricity needs might find rooftop or ground-mounted solar the simplest and most cost-effective option. A farm in a windy plain state might benefit from wind, either through on-farm turbines or leasing land for utility-scale development. A large dairy or livestock operation with substantial manure production and high, continuous energy needs might find biogas the most economically and environmentally compelling choice. In many cases, a combination makes sense. Solar for daytime power, biogas for baseload and dispatchable generation, and battery storage to smooth out variability. The optimal energy system for a farm is rarely a single technology, but rather an integrated portfolio that matches the farm's resources, needs, and constraints. One of the most profound benefits of on-farm renewable energy, whether solar, wind, or biogas, is the degree of energy independence it provides. For farmers who operate in an industry characterized by price volatility, weather uncertainty, and economic pressures, gaining more control over their energy supply represents a significant strategic advantage. Let's think about what energy dependence means for a typical farm. You're relying on fuel deliveries for your tractors and equipment. You're subject to electricity rates set by your utility, which can change annually or even seasonally. You're vulnerable to supply disruptions. A severe storm damages transmission lines, and your dairy loses power for hours, threatening your herd and your milk quality. Global events cause oil prices to spike, and your diesel costs double, but you can't simply stop irrigating your crops. That lack of control is a source of risk and stress. Farmers are expert risk managers out of necessity, hedging against weather, pests, disease, market fluctuations. But energy has traditionally been one risk factor they've had limited ability to hedge. On-farm energy generation changes that dynamic. A farm with sufficient solar, wind, or biogas capacity can meet all or most of its electricity needs from its own generation. That farm is insulated from utility rate increases. If electricity prices rise 30% over 5 years, the farm with its own generation sees minimal impact. In fact, if they're selling excess power back to the grid, they benefit from rising electricity prices. For off-grid or remote farms, renewable energy combined with battery storage can eliminate the need for grid connection entirely. In regions where extending grid power to remote agricultural operations costs tens or even hundreds of thousands of dollars, an off-grid solar plus battery system can be far more economical. And even for grid-connected farms, having on-site generation and storage provides resilience against outages. Consider a broiler chicken operation. Those chickens require precisely controlled temperature and ventilation. If power goes out for even a few hours in hot weather, the flock can suffer catastrophic losses from heat stress. Traditionally, the farm relies on a diesel backup generator, but generators require maintenance, fuel storage, and they only run during outages, providing no value the rest of the time. A solar plus battery system, or a biogas powered generator, provides both daily operational power and backup capability. The investment works for the farm every single day, not just during emergencies. Energy independence also has national and regional security dimensions. Farms that generate their own power reduce overall demand for imported fossil fuels. In a country like the United States, which has pursued energy independence as a strategic goal, distributed renewable energy on farms contributes to that objective. During crises, whether natural disasters, geopolitical conflicts, or pandemics, farms with energy independence can continue operating even when broader infrastructure is disrupted. That's food security. There's a psychological and cultural dimension too. Farmers value self-reliance. Being able to power your operation from resources you produce on your own land aligns deeply with agricultural values. It's empowering. It reinforces a sense of stewardship and control over your farm's destiny. Of course, complete energy independence is challenging and may not be economically optimal for all farms. Most farms that generate renewable energy still maintain grid connections for reliability and for selling excess power. But even partial energy independence, meeting 50% or 75% of your needs from on-farm generation, significantly reduces vulnerability and provides substantial economic and strategic benefits. Agriculture is both a contributor to climate change and a sector that will be profoundly affected by it. Globally, agriculture accounts for roughly 10 to 12% of greenhouse gas emissions. In the U.S., agriculture represents about 9% of total emissions. These emissions come from multiple sources: methane from livestock digestion and manure, nitrous oxide from fertilizer application, carbon dioxide from farm equipment and energy use, and emissions associated with land use changes. At the same time, agriculture is uniquely vulnerable to climate impacts. Changing precipitation patterns, increased frequency of droughts and floods, shifting growing seasons, new pest and disease pressures, all of these threaten agricultural productivity and farm livelihoods. This creates both responsibility and opportunity for the agricultural sector. Farms can be part of the climate solution through practices that reduce emissions and sequester carbon. Renewable energy adoption is a key piece of that puzzle. Let's quantify the impact. A dairy farm that installs a biogas digester and eliminates methane emissions from manure storage might prevent the equivalent of several thousand tons of carbon dioxide from entering the atmosphere annually. That's comparable to taking hundreds of cars off the road. If that same farm powers its operations with biogas-generated electricity instead of grid power, which in many regions is still predominantly fossil fuel-based, there's an additional emissions reduction from displaced fossil electricity. A crop farm that transitions from diesel irrigation pumps to solar-powered systems eliminates direct combustion emissions from fields. Over a 20-year period, that could represent hundreds of tons of carbon dioxide avoided, plus the reduction in particulate matter and other air pollutants from diesel exhaust. Wind turbines on farmland, whether owned by the farmer or leased to a developer, generate clean electricity that displaces fossil generation somewhere on the grid. A single modern wind turbine can generate enough electricity over its lifetime to offset tens of thousands of tons of carbon dioxide emissions compared to coal or natural gas generation. Cumulatively, if a significant fraction of farms adopted renewable energy systems, the climate impact would be substantial. Agriculture could shift from being a net emission source to being closer to carbon neutral or even carbon negative, particularly when combined with other practices like cover cropping, no-till farming, and agroforestry that sequester carbon in soils and biomass. Importantly, renewable energy on farms doesn't require compromising productivity. You can maintain or increase crop yields and livestock production while dramatically reducing your carbon footprint. That's a key point. Climate mitigation in agriculture isn't about producing less food. It's about producing food more intelligently and sustainably. There are also adaptation benefits. Farms with diversified energy sources and energy independence are more resilient to climate-driven disruptions. If extreme weather damages grid infrastructure, farms with on-site generation and storage can continue operating. If fuel supply chains are disrupted, farms with solar or biogas aren't stranded. The broader food system benefits as well. A more climate-resilient agricultural sector means more stable food supplies and prices. It means reduced risk of climate-driven food crises. Given global population growth and the imperative to feed 9 or 10 billion people by mid-century, ensuring agriculture can thrive despite climate change is critical. Renewable energy adoption is one tool in that larger toolbox. Given all the benefits we discussed, economic, environmental, strategic, you might wonder why every farm hasn't already installed solar panels, wind turbines, or biogas digesters. The reality is that significant barriers still limit adoption, and understanding these barriers is essential for addressing them. The most obvious barrier is upfront cost. Renewable energy systems require substantial capital investment. For a farm operating on thin margins, finding $200,000 for a solar array or $2 million for a biogas digester is daunting, even if the long-term payback is favorable. Many farms don't have that kind of capital sitting idle, and taking on significant debt is risky, especially in an industry where income can vary dramatically year to year, depending on weather and commodity prices. Financing options exist: loans, leases, power purchase agreements, but accessing them can be complex. Rural banks may not have experience evaluating renewable energy projects. Loan officers accustomed to financing land or equipment may be unsure how to assess the risk and return of a solar installation. This financing gap means some economically viable projects don't move forward simply because the farmer can't access appropriate capital. Technical knowledge is another barrier. Most farmers are not electrical engineers or energy system experts. Understanding how to design, specify, install, and maintain a solar array or wind turbine requires expertise that's outside traditional agricultural knowledge. While contractors and installers exist, finding quality providers in rural areas can be challenging, and farmers rightfully worry about being oversold on systems that don't perform as promised or that require more maintenance than they were led to believe. Biogas systems are particularly complex. Operating an anaerobic digester requires understanding microbiology, chemistry, mechanical systems, and energy management. It's a steep learning curve. Some farmers thrive on that technical challenge. Others find it overwhelming, particularly older farmers who may be less comfortable with new technologies. Permitting and regulatory complexity is another hurdle. Installing renewable energy systems often requires navigating local zoning regulations, building permits, electrical interconnection agreements with utilities, and environmental permits. For biogas systems that process waste, environmental regulations can be particularly stringent. The bureaucratic burden can be substantial, requiring time and often legal or consulting support that adds to costs. Interconnection with the electrical grid can be especially frustrating. Utilities may have technical requirements for how renewable energy systems connect, require expensive upgrades to local infrastructure, or impose charges and restrictions that undermine project economics. Some utilities are highly supportive of distributed renewable energy. Others are resistant, viewing it as a threat to their business model. The farmer is caught in the middle, trying to navigate utility politics and procedures. Maintenance and reliability concerns are real. Renewable energy systems generally require less maintenance than diesel generators, but they still need attention. Solar inverters fail. Wind turbine gearboxes wear out. Biogas digesters can have microbial upsets or equipment failures. If the farmer doesn't have in-house expertise, they're relying on outside technicians, who may be hours away and charge premium rates for service calls. Downtime means lost production, whether that's electricity not generated and sold, or farm operations hampered by lack of power. There's also inertia and risk aversion. Farmers, like anyone, are more comfortable with what they know. They understand diesel tractors and grid electricity. Those are proven, familiar technologies. Renewable energy, even though it's mature and widely deployed, feels newer and riskier to many. The "if it ain't broke, don't fix it" mentality can be strong, especially among older farmers who may not plan to farm for another 20 or 30 years, and thus don't expect to see the full payback period of a renewable energy investment. Cultural and social factors play a role too. In some rural communities, renewable energy is politically or culturally controversial. Some people view solar panels or wind turbines as ugly, or as associated with urban environmental politics that feel disconnected from rural agricultural values. A farmer who installs visible renewable energy infrastructure might face criticism or social pressure from neighbors or community members. That social risk can be a real deterrent. Finally, there's the challenge of split incentives. On rented farmland, the farmer who works the land may not own it. Why would they invest in permanent infrastructure like solar panels if they don't own the property and could lose their lease? Similarly, landowners may not invest if they're not the ones operating the farm and paying the energy bills. This landlord-tenant dynamic can freeze decision-making. Given these barriers, government policy plays a crucial role in accelerating renewable energy adoption in agriculture. And indeed, numerous federal, state, and local incentives exist, though navigating them can be complex. At the federal level in the United States, the investment tax credit and the production tax credit have been major drivers of renewable energy deployment. The investment tax credit allows farms to deduct a percentage of the cost of solar installations from their federal taxes. As of recent legislation, the credit is 30% through 2032, then steps down in later years. For a farm installing a $400,000 solar system, that a $120,000 tax credit, dramatically improving project economics. The production tax credit applies primarily to wind energy, providing a per kilowatt-hour credit for electricity generated over the first 10 years of operation. For farms generating and selling power, this creates a steady, predictable revenue stream that improves financing and payback calculations. The USDA offers several grant and loan programs specifically for rural renewable energy. The Rural Energy for America program, commonly called REAP, provides grants and loan guarantees for renewable energy and energy efficiency projects. REAP grants can cover up to 25% of project costs, which when combined with tax credits, can bring total incentives to 50% or more of the project cost. That transforms the economic calculus from marginal to highly favorable. State-level incentives vary widely. Some states offer additional tax credits, rebates, or grants for renewable energy. States with renewable portfolio standards that require utilities to source a certain percentage of their power from renewables create markets for the electricity that farm-based systems generate. Net metering policies, which compensate farms for excess electricity they send back to the grid, significantly affect project economics. States with favorable net metering allow farms to use the grid essentially as a battery, sending excess power during the day and drawing it back at night, with financial settlement that makes the exchange fair. California's low-carbon fuel standard deserves special mention. This policy provides substantial credits for renewable natural gas produced from farm biogas and used as transportation fuel. The credits can be worth tens or even hundreds of thousands of dollars annually for a biogas project, making California one of the most economically attractive states for farm biogas development. Carbon credit markets represent an emerging incentive mechanism. Farms that reduce greenhouse gas emissions through practices like biogas production, cover cropping, or reduced tillage can generate carbon offset credits that are sold to companies or individuals seeking to offset their own emissions. Carbon credit prices vary by market and project type, but they can provide meaningful additional revenue. A dairy digester project might generate credits worth $50,000 to $100,000 annually, depending on the size of the operation and the methane reductions achieved. However, carbon credit markets are complex and somewhat fragmented. Different registries, standards, and methodologies exist. Transaction costs can be high. For smaller farms, the administrative burden of quantifying, verifying, and selling carbon credits may outweigh the value. Aggregators and project developers have emerged to help farmers navigate the space, pooling credits from multiple farms to achieve economies of scale. Policy stability matters enormously. When incentives are predictable and long-term, farmers and investors can plan accordingly. When incentives expire, get extended at the last minute, or change unpredictably, it creates uncertainty that chills investment. Advocacy for stable, long-term renewable energy policies in agriculture is ongoing. There's also room for innovative policy design. Some proposals suggest creating preferential incentives for smaller or beginning farmers who face the greatest barriers to accessing capital. Others propose regional or cooperative development models where multiple farms can jointly access incentives. Linking agricultural renewable energy support to broader climate and conservation programs could create synergies and more comprehensive support packages. International comparisons are instructive. Germany's feed-in tariffs guaranteed attractive prices for renewable electricity for 20 years, creating massive deployment of farm-based biogas. Denmark similarly used policy to build a robust biogas sector. These countries demonstrate that well-designed policy can rapidly transform agricultural energy systems. Let's conclude by looking forward. Where's agricultural energy headed? What will the farm of the future look like from an energy perspective? The trajectory is clear. Farms are becoming smarter, more integrated, and more energy independent, and the pace of change is accelerating. Smart energy management systems are already emerging. These systems use sensors, weather forecasts, electricity price signals, and AI algorithms to optimize when and how energy is used and generated on a farm. Imagine a dairy farm with solar panels, a biogas digester, battery storage, and grid connection. A smart energy management system monitors all these assets in real time. It forecasts solar production based on weather. It schedules energy-intensive operations, like running pumps or grain dryers, for times when solar production is high or electricity prices are low. It decides on to charge or discharge batteries to maximize value. It even coordinates with the grid to provide services like demand response, getting paid to reduce consumption during peak demand events. This isn't science fiction. These systems exist and are becoming more sophisticated and affordable. Artificial intelligence and machine learning enable these systems to continuously improve, learning from patterns and optimizing over time. For farmers, this means maximizing the value of their energy assets with minimal manual intervention. Integration is another key trend. The future farm energy system isn't just solar, or just wind, or just biogas. It's a hybrid system that leverages multiple energy sources, storage technologies, and flexible loads. Solar provides daytime power. Biogas provides baseload and dispatchable generation. Batteries store excess and provide backup. Electric vehicles and equipment serve as both loads and potential mobile storage. The grid acts as a balancing resource. This integration extends beyond electricity. Combined heat and power systems capture waste heat from generators and use it productively. Thermal storage allows heat to be stored and used when needed. Renewable hydrogen, produced from excess renewable electricity, could become a storage medium and a clean fuel for equipment that's difficult to electrify. The concept of the virtual power plant is particularly exciting. Individual farms with renewable generation and storage are relatively small players in energy markets. But aggregate hundreds or thousands of farms together, and you have a substantial, distributed power resource. Virtual power plant platforms are emerging that coordinate distributed energy assets, presenting them to grid operators as a single, reliable resource. Farms get compensated for their participation, and the grid benefits from flexible, distributed capacity. It's a win-win that unlocks value farms couldn't access individually. Electrification of farm equipment is accelerating. Electric tractors, UTVs, and tools are entering the market. As battery technology improves and costs fall, we'll see larger equipment electrify. This creates new load flexibility. Electric tractors can charge when renewable generation is high and electricity is cheap, then discharge battery power during field operations, or even back to the farm or grid when needed. Precision agriculture and energy are converging. Sensors monitor soil moisture, crop health, and weather conditions in real time. That data feeds into decision systems that optimize irrigation, climate control, and other energy-intensive operations, using only as much energy as needed, precisely when and where needed. The result is reduced energy waste and improved productivity. The net zero farm is the ultimate goal. A net zero farm produces as much energy as it consumes over the course of a year. It may still draw power from the grid at certain times, but over the full year, its own renewable generation equals or exceeds its consumption. Some farms are already achieving net zero or even net positive status, where they generate more energy than they use and become net exporters. Achieving net zero requires a comprehensive approach. It's not just about adding solar panels. It's about improving energy efficiency, reducing waste, optimizing operations, deploying multiple renewable technologies, and integrating storage. But the technologies and economics to achieve this are increasingly within reach. Beyond net zero electricity, there's a vision of net zero or carbon negative farming more broadly. Farms that sequester carbon in soils through regenerative practices, produce renewable fuels from biomass, eliminate fossil fuel use in equipment and operations, and produce renewable energy for export. These farms become climate solutions, actively pulling carbon from the atmosphere while producing food. Policy and market forces are aligning to support this vision. Corporate commitments to carbon neutrality are creating demand for carbon credits and renewable energy from agriculture. Consumer demand for sustainably produced food is growing. Investors are increasingly interested in climate-smart agriculture. Government climate policies are beginning to recognize and support agriculture's role in decarbonization. The economics continue to improve. Renewable energy costs keep falling. Energy storage is becoming affordable. Smart technologies reduce the complexity and labor burden. Financing options are expanding. The business case for farm-based renewable energy gets stronger every year. Cultural shifts are happening too. Younger farmers, digital natives comfortable with technology, are more open to innovation. Agricultural education is increasingly incorporating energy and sustainability topics. The perception of renewable energy in rural communities is gradually shifting from skepticism to acceptance and even enthusiasm as successful examples proliferate. Looking 20 or 30 years ahead, it's entirely plausible that the majority of farms will be significant energy producers, that rural areas will be energy exporting regions powered by distributed renewables, that agriculture will be a net contributor to climate solutions rather than a net emitter. The farm of the future is energy smart, climate positive, economically resilient, and technologically sophisticated. We're in the early stages of this transformation. The pioneers are proving what's possible. The technologies are maturing. The economics are improving. The policies are evolving. The path forward is increasingly clear. Agriculture and energy, two foundational pillars of civilization, are converging in ways that promise a more sustainable, secure, and prosperous future for farmers and for all of us who depend on the food they produce. And that concludes our second segment on energy in modern agriculture. We've explored biogas and anaerobic digestion, the dual benefits of waste management and energy production, the value of digestate as fertilizer, how livestock farms are becoming energy hubs, how to compare different renewable energy options, the strategic value of energy independence, agriculture's role in climate solutions, the barriers holding back faster adoption, how policy and incentives are accelerating change, and finally, the exciting vision of smart, integrated, net zero farms of the future. Energy isn't just an input cost for agriculture anymore. It's an opportunity, a strategic asset, and a pathway to a more resilient and sustainable food system.